Okay. Okay, so welcome to class 13 of this course, page 576, Statistical Mechanics. So we had derived this, no? This Ni star, the most probable occupation number for all the three statistics. How many of you remember this? I hope you remember.
Yes, sir.
Yeah. So if I consider, for example, Fermi Dirac, then what is the value of A? Is 1. Bose-Einstein, it is -1. And Maxwell-Boltzmann is 0. The general structure, isn't it? That was the general structure, and we had already derived. Is this clear?
Yes, sir.
So now we'll just concentrate ourselves to say do later, but in general, let us do this. Let us calculate entropy. Entropy divided by Kb. What is there on your right hand side? It should be ln omega, isn't it? And if you
Yes, sir.
notes, you will see that ideally you should have the sum over all possible configurations. You have this capital W, no? And how do you approximate this? You approximate this with W with most probable Ni, isn't it?
Yes, sir.
And also, you know, this capital W is a product of small w's. So you have log. So this will become something like a small w omega, whatever you want to call it. This is the expression for entropy. Okay, this is very straightforward. So let me calculate this expression. It is going to be ln. Now this w, whatever, you know, all these things. Okay. Now, if I go back to the previous class notes, what is w? How many of you remember? This is how it is, isn't it? Go and check your class note. It was there, no?
Yes, sir.
So you just have a look at the class note. So we'll see that this is exactly what you have, isn't it? So I'm now going to make use of this. So what I'm going to do, instead of ln small w, I'll put this expression. This expression is something like, you know, ni ln gi by ni minus a, okay, minus gi by a ln 1 minus a ni by gi. Now you have to, you know already that these ni's are actually ni star, isn't it?
Yes,
All
sir.
these ni's. I put it there. So the next what I do, I just replace these ni stars with the expression shown here. Not everywhere, in some places, so that I can manipulate my calculations. This ni star I don't touch, I put it like this. Take this gi. Now you know gi by ni star. What is the expression actually? I can directly put it
A
here.
plus C power alpha.
Because, you know, gi by ni star is this. You can take on the other side, isn't it? The expression. So you'll have something like a plus whatever u of alpha plus beta epsilon I minus a, isn't it? What is the next term? Next term is you put a second bracket here, angular bracket. Gi divided by a ln, again 1 minus a into ni star by gi. Ni star by gi is again, ni star by gi is what?
1 by A plus C power alpha plus beta A.
Okay, so the first term becomes what? It's very easy.
Alpha
It is
plus
an
beta
NA
A.
star. Now this A and A will cancel, no? And log of this. So you'll get alpha plus beta epsilon I. Is this clear? I hope this is clear.
Yes, sir.
What about the next term? Now let us see what is the next term. Next term is you have minus gi by a ln. So you do this. This will give me this is fine. Again, this thing will
Yes.
cancel. These things will cancel, isn't it? And the next, I can write it like as follows. Minus gi by a. So this is ln x by y. So I can always write as minus of ln y by x, isn't it? Can I do that? Just ln x by y. Isn't it? I hope this is fine. So
Yes,
this will
sir.
give me another minus here, and this term will become ln. Let me write down one more time. So now I can further simplify this. If I further simplify, what I'm going to get? I'm going to get and you know this is actually a by this plus 1, isn't it? This is what I'm going to get is ln 1 plus a is this clear? I hope this should be clear.
No.
This is how it is. No, very simple thing, and we'll need this. So I will need this. Uh, this is my expression for entropy. But you know that when I started, we had two constraints. What are those constraints? You know, the ni is this, whatever, isn't it? We had this constraint that ni star, what is, it should be equal to n, isn't it? So if I multiply this with alpha, what I'm going to get? What is this? This is alpha into n, isn't it? So similarly, I had another constraint. What is that constraint? How many of you remember?
Omega I Ni epsilon I is equal.
Yeah. So this has to be equal to, I think what notation I use, capital E, isn't it? So similarly, if I multiply this with beta, I get beta E. So the first two term, what I'm going to get from the first two term, will give me alpha n plus beta E. Is this clear? Is this clear? Please say
Yes.
yes. Yeah, this is not a very difficult
Yes,
thing.
sir.
And then I have this term left. Okay. So I can always write that this term gi by a log of 1 plus a minus alpha minus beta epsilon I. is equal to S by Kb. This is fine. If I write like this is fine, I hope.
Yes, sir.
And we had done earlier. We know what is alpha. If you see your previous note, it is this. You can similarly you can find what is the value of beta is done earlier. Not with bosons or fermions, but for Boltzmann statistics, it is done. So you can just borrow the values of alpha and beta from there. Okay. So if I borrow the values of alpha and beta from there, what I'm going to get something like S by Kb. This will give plus mu by mu n by Kbt minus E by Kbt, that is equal to okay. This is fine.
Yes, sir.
What is this mu into n? If you have one single component, you know this is gives free energy, isn't it?
Yes.
So can I further simplify this? Yes, I can. What you can do? What I can do is as follows. Okay. I think I should have a sum, no? You must have, you should have told me. There is a sum, isn't it? Gee, I should be inside. Okay. Now, I know that if I multiply this with kbt, what I'm going to get? Ts, whatever, Ts plus mu n minus E equals to kbt by A sum over I ln 1 plus A Now, what is this? This quantity on your left.
Sir, GI is missing inside.
Yeah. So what is left on your? What is this on your left? Just look carefully. What is this? This is G, and you know what is this? Ts plus G minus E. Any idea? What is that? What is that? What is G?
PV? Is it PV?
Yeah, it has to be PV. So this quantity is nothing but PV. You have PV. You know that, no? You
Yes,
know
sir.
that it is PV.
Yes, sir.
Because you know this is equal to, other way I can write, it is E plus PV minus Ts. No, from there I can write. So what I have here is PV equals to kBT by A and this is actually what is known as equation of state for a quantum. You have A here, of course. Okay, so I don't think we had done this earlier. This is equation of state for quantum ideal gas. Is this clear?
Yes, sir.
Now what you should get what is known as uh, Maxwell-Boltzmann distribution. Not sorry. What will happen if it is classical gas? What is the equation of state?
PV equal to NKBT.
Yeah, P equal to kVt, isn't it? Has to be.
No, yes.
NKVT, yeah, has to be. So how do you get this? See, the point is as follows. In the Maxwell-Boltzmann case, what happened that your A goes to 0, isn't it? So this quantity is small actually. We'll talk about it later also in more detail, okay? If it is small, so this thing becomes kBt by A sum over I Gi. You know what is ln 1 plus x in the limit x goes to 0. What is the answer? This is how it is, isn't it?
Yes, sir.
And so this is equal to this A will cancel. What you have here is kBt okay. But what is this? This is Ni star for Maxwell-Boltzmann, isn't it? You guys go and check your
Yes, sir.
expressions. So what I have here is so sum over Ni star has to be equal to n, total number of particles. So what I have is, I think capital P I'm writing, ideal gas law, isn't it?
Yes, sir.
But classical, okay? That's why it follows Maxwell-Boltzmann distribution. Okay, is this clear?
Yes, sir.
Yes.
Okay, now let us consider what is known as ideal Bose gas. Now, what is an ideal Bose gas? You know the value of A is equal to what? What is the value of A?
Minus 1.
Minus 1. Why ideal Bose gas? Because these particles or these atoms, whatever, are non-interacting. This is exactly what it is, isn't it? So you have n number of bosonic atoms or bosons, but they are non-interacting. This is called ideal Bose gas. Okay, so they're quantum particles, but what kind of quantum particles? They're bosons. They follow Bose-Einstein statistics. It's not very difficult. I hope you are following.
Yes, sir.
So what will happen to my equation of state? My equation of state is now PV by kVt, if I write like this, is minus so let us define something. We know alpha, which is known as of sorry exponential mu by kBt, and this is I'm calling small z, and this is called fugacity. Okay, let us define this fugacity. If I define this fugacity, my equation of state becomes Okay, I hope you're following.
Yes,
It's
sir.
not very difficult.
Yes, sir.
So this is here, the sum is over what? Energy levels. Okay, so in the next step, what I'm going to do, I'm replace this sum as not, so replacing the sum over energy levels with the sum over states. And then replacing the sum with an integral giving a statistical weight to each state. Okay, so what I had, let me go and see. We had something like this. Okay, I can write here actually. Let me use this. Yeah. So we had something like PV by kVt. Which is, I think we have already introduced fugacity. So I had something like I hope that was the expression, isn't it?
Sir, a minus sign.
Minus should be there, yes. Okay. So this is the expression we had, no? Just go and check. This is the expression we had for bosons.
Yes,
And
sir.
then I am replacing this with an integral. So this is what I'm going to write. I'm going to write an integral. Quantity is something like ln 1 minus z exponential and minus beta epsilon I. Ideally, I should integrate over epsilon. But before I do that, I should actually multiply this with something what is known as density of states. This is very important. Okay. So basically density of state is what? So is actually number of states between,
Epsilon and epsilon cross d epsilon.
yes. So I just, so I have to give a statistical weight factor, statistical weight, and then I have to calculate this density of state. Then I have to calculate this PV by kVt. Okay, is this clear?
Yes, sir.
Sir,
Similarly, yeah.
Sir, is there any pretext for this for changing summation to integration, like the temperature or something?
Yes, I did
Yeah.
not say this here. Either high temperature or large volume. We'll talk about it later. Okay. Either high temperature, low density, or large volume. Then only the levels will be very close to each other, and you can replace the sum by an integral. Okay. So this is one quantity you can calculate. You can calculate one more quantity. What is this? You know that n, total number of particles, I can always write it as something like sum over ni, isn't it? And this is going to be, what is the expression of ni? Average. You remember, no? Ni average. What was the expression? It was gi. I go back.
GI.
Yeah, just to show you. This is the expression, no? Gi by whatever. This
Yes.
minus 1. It is equal alpha plus beta epsilon I minus 1. Has to be like this. So this is, I know you have defined a quantity called fugacity. So this one is going to be gi divided by z inverse, and then I can say this is equal to integral. You know, this integral is going to be, again, it just replace that integral by this d epsilon e divided by 1 over z. Shut up. It will be like something like that, isn't it? It has to be like this. Okay.
Yes, sir.
Now, how to calculate density of states? How do you calculate? Say, go back to 3D box. Particle in 3D box. What are the expression for energy? E. That is the expression, E. Or okay, I can use a different notation. Epsilon. What are the expression? You remember this?
X square plus ny square plus nz square.
Yeah, I assume it's a cubic box. Into,
First square.
this is how it is, isn't it? It has to be like this.
Yes, sir.
So I can always think of, if it is in 2D, I can think this is your ny axis, this is nx axis. So I can think of a circle of radius r. And then you have many lattice point here. And I calculate number of lattice points. Okay. Now, what is r? You know, r is
Root
this.
over nx square.
So r square is this, isn't it? Like your r square is what? R square is your 8 m l square, sorry, l square into epsilon by h square is your r square. So this is equal to nx square plus ny square plus nz square, isn't it? I just show two axes here. Okay. So
Yes.
how? So if I calculate the number of such states, how many number of such states are there? Can anyone guess? There's one restriction is there. This nx, ny, nz. This restriction is there, no? isn't it? It
Yes,
cannot be
sir.
negative. Also, it cannot be 0, but it cannot be negative, isn't it? Huh?
Yes, sir.
So what should be the number of states? Can you calculate? This is number of states means number of points. So actually, if I can calculate the volume of, for example, if the as my R increases, number of states should increase.
Yes, sir.
Right, sir.
So it should be proportional to the volume of this sphere. And a good, very good way of writing would be like 4/3 pi R cube.
Cube.
This could be the number of such state, isn't it? Yes, but it is not exact. It is not strictly. This is not the number because I have to multiply this with 1/8. Why 1/8? Only 1 octane I take. Any idea? Why we take only 1 octane?
Because of the restriction in X and Y and Z.
Yes, because of this restriction. So this is a good way of saying. Then this is equal to what? Equal to 1/8. 4/3 pi. What is R cube? R is this. So R is this. R cube is this is R cube, isn't it? So what you get here is pi by 6. But now I have to calculate. I can calculate this phi at E plus say delta E. What will the answer? Something, no? It will be something. I can just put this expression and instead of epsilon, not E, sorry, epsilon. You put epsilon plus del epsilon, isn't it? But then what we are really interested is in this. Sorry. That what is the number of states between energy epsilon and epsilon plus delta epsilon? So we are interested in this. Is this clear?
Yes,
So
sir.
basically, you can think of a value number of states with energy E plus delta epsilon, sorry, epsilon plus delta epsilon, also slightly less with epsilon, because the condition is that your delta epsilon by epsilon is very, very small. And what is this? I can approximate this as isn't it?
Yes, sir.
This is going to be 5 prime. 5 prime, you know what does it mean? 5 prime means then what will be the answer? You know phi epsilon, sorry, it's 5 epsilon is this. Then what is 5 prime? 5 prime is going to be this. The prefactors are there. Okay. And then it will be 3 by 2 epsilon 3 by 2 minus 1. Isn't it?
Yes,
So
sir.
this will give me, of course, you have a delta epsilon here. So this will give me, this 3 and 6 will cancel. This will give you pi by 4. Isn't it?
Yes, sir.
8m. 8m by h square to 3 by 2. 3 by 2 L cube epsilon half delta epsilon. Is this clear? I can further simplify this actually. So LQ, I can call it some volume, no? It has some volume V.
Yes, sir.
V is your LQ, the volume available to these gas particles. And then this thing you can actually you can simplify these things. And if I simplify these things, so I'm just wondering whether I'll have, if I write like this will give me 8 means
8
I
power.
hope this is fine, na? Because I just like okay, I'll go to the next slide and show what I'm going to write. I'm going to write this PV by kVt, and if I write it like this, and also it is possible to show that this G epsilon, D epsilon, whatever I've calculated, is actually twice pi V by H cube into twice m to the power 3 by 2 epsilon half. Here I have D epsilon. You can check this. I hope this will match.
Yes, I think it follows.
Yeah. So if I then I can write down like this. No, this one is going to be minus this. I'll have the whole thing here multiplied with ln 1 minus the exponential of minus beta epsilon. Okay, is this clear? This is how
Yes.
it should be. This is how it should be. Now, before we proceed, I want to tell you one more thing. What is that? So, because if I calculate this, your whatever n, yeah, your n k average. If I use k, what are that expression? If I assume g, I just don't take g. If you want, you can take g. Doesn't matter. It is if I go back to this expression, this is the expression. No? This is the expression, isn't it? This is the expression. I can multiply this with like z exponential of minus beta e. If I multiply it with like z exponential of minus beta epsilon k, I'm using k here. This will, the first one will give you 1 minus, this is for fermions. It's not for fermions, it's for bosons, isn't it? Because I want to make a general statement here. Very important that I make it. Okay. Yes. There's a time lag. And you know that this is for BE, and if I calculate for Fermi-Dirac, this is going to be something like now. Look carefully what happens if for example temperature is high or density is low. What do you expect? Density means number of particles per unit volume. No, this is your density. What do you expect? In this case, what will happen that if your temperature is high or density is low, temperature is not so high, what will happen in that case? In that case, number of available energy states is going to be much greater than number of particles. If you have problem, please tell me. Your temperature is high. You have collection of particles. Temperature is high. So the particles could be anywhere. It can have any energy because the temperature is high. So the particle could be, you can put the particle at higher energy states, isn't it? Number of available energy states is much greater than number of particles. Okay?
Sir,
Yes.
can you explain density in terms of density when density is low?
And when density is low, density is low means it's same thing, because when density is low, it basically means that you have a huge volume, and then in huge volume you have only few particles sitting around. So density is low means, for example, if I go to particle in a box problem, what happens? If your density is low, basically means your volume is high, isn't it?
Yes, sir.
Volume is high, your length is high. What happens to your energy levels? Energy levels are,
Closely
Number of
spaced.
energy. Closely spaced.
it is 1 over L square. No, it's 1 over L square.
Yes, sir.
It's 1 over L square. So the energy levels are going to be closely spaced, isn't it? When density is low,
Yes, sir.
Yes, sir.
it has to be. So you will see that very closely spaced energy levels are there, but actually your temperature is high or density is low. Then you see the number of, at that temperature or with that density, the number of available energy states is much more than number of particles. You understand? Accessible energy states are huge in number compared to the number of particles. Think about this situation. The number of particles is huge but finite. But if your temperature is high or the density is low, your energy spectrum is such that under such condition, the number of available energy states is much greater than number of particles. Because you have more, you can just say, for example, your available energy state is 1 billion and you have 1 million particles. It's like that. With at that energy, at the temperature. Okay, think in terms of temperature, for example. Okay, so what is going to happen then? Anish, can you tell me what do you expect then about the occupation? Is nk. What will be the average value of nk average? Think of a situation that I have 10 particles but I have, say, 1000 energy levels. This is the situation. You understand what I'm saying?
Yes.
So what will happen? Then you cannot satisfy all the energy levels, isn't it?
Yes.
Most of the energy levels will be vacant, will not have any particle. So what will happen to this average nk? So it does not really matter whether you're dealing with fermionic system or bosonic system, isn't it? Because available states are much more in number than the number of particles.
Yes.
So what will happen? You'll have rarely have a situation where you have a what is that called? You have a case where a particular energy state has more than one particle. So either the state has one particle or no particle, like this. And then many instances there is no particle. So what will happen to this nk average? This nk average has to be very
Both
small.
will be same.
Very small. Because nk average means what? Is average number of occupation is going to be very close to 0. It has to be. See,
Yes.
if I have 10,000 energy states and I have 10 particles, then the average occupation number has to be very small, isn't it? Almost 0.
Yes.
It is like,
Yes,
so
sir.
it does not matter whether it's Fermi-Dirac or Bose-Einstein. So at high temperature or low density, so this quantum thing is vanishing. The quantum nature, the quantum mechanical aspect is missing. You understand? So in that case, your nk average doesn't matter. Fermi-Dirac, Bose-Einstein, this will be 0. So this is possible when? This is actually the case where your Z, this fugacity goes to, tell me.
0.
Goes to 0. because in that case your NK average is going to be and this is called weakly degenerate case. This is fine, huh? Because 1 minus this is small, so I neglect. Huh?
Yes. Yes, sir.
Okay, this is fine. So is it consistent with your it is consistent with your Fermi-Dirac sorry Boltzmann Maxwell-Boltzmann statistics, no? Because if I take average of this sum of this, what I'm going to get? And this is something like a partition function, small z times q, isn't it? So your NK average, you can write it like as, of course, and this is actually number of particles. So your NK average, you can write it as your NK average is z exponential of minus beta k. So we have this. Okay, but I know that z is going to be n by q. So I have, and what is this? You guys already know this, isn't it? If I write like this, you know.
Yeah. Average number of particles.
This, I think you are familiar with this expression, isn't it?
Yes, sir.
Yes,
The
sir.
number of particles. This is the classical limit, high temperature limit. So basically, this is Maxwell-Boltzmann. So when T is high or density is low, you get classical, you hit classical limit. Okay, is this clear? So it does not matter whether you start with a Fermi gas or bosonic gas. Okay, when the temperature is high, both of them will behave like classical gas, which is following Maxwell-Boltzmann distribution. Very important. Very important. This is very important.
Sir, hello, sir.
Yes.
Sir, could you please define fugacity? Like physical sense, what does it mean actually?
So basically what I have here in fugacity is like this. It is not very easy to explain fugacity because I need more classes. But what I can tell you that fugacity is defined as like this. No, Z is exponential of mu by kVt. So if fugacity goes to 0, I am going to classical limit. Okay, and if fugacity is greater than 0, high, then I am hitting quantum. So fugacity is a measure of how much your gas is deviating from its classical description. So any non-zero Z is a signature that your gas has some kind of quantum nature in this case. So if you go to high temperature, low density, fugacity is 0. But if you go to the other limit, the fugacity will be high. You understand what I'm saying?
Yes, sir.
So your fugacity will become 1 actually if you go to low temperature, and if you go to high temperature, your fugacity becomes 0. Okay.
So the limit is 0 to 1.
It is 0 to 1. It's 0 to 1. Okay. So if I get time, we'll discuss, but I have many things to discuss. So we'll do this thing qualitatively. But now I'll go back to your equation of state for the Bose gas. So So your equation of state
So,
for the Bose gas.
we have gone through fluidity. Is it something related to deviation from the ideality?
Yeah, that is a different thing.
Okay.
Here it is the deviation from the classical.
Okay.
Here I am comparing a classical with a quantum gas. Okay.
Okay.
Using the same word, but it is different. So now PV by kBt has now become minus okay. So now if I write like this, I have a problem. One problem is there. What is that problem? The state epsilon equals 0 has been given 0 weight, isn't it? Because epsilon to the half, no? And this is not acceptable. So we should take this state out and then replace the sum with an integral. With the integral. So if I do that, because I cannot say that the lowest, then it is 0 weight means what? It has no weight. I cannot be partial like this, isn't it?
Yes, sir.
So this is the way to think about. So what should be the answer then? Then if I do this, your P by say kBt, it is going to be, I can tell you, so this part will be there minus see there is V here, I don't think it's V is there. Yeah, it's fine. It's fine. So P by kBt, this V will go. Ideally, I should write this integral from like 0 plus, but I am writing 0. Huh? This is not full thing. What I have to add then? I have to add something else. What is that? I have to write this epsilon equal to 0 state separately. And if I write it down, what is going to be for that state? You remember, you go back to your expression, the sum. Where was it? It is here. Essentially, I have to take this expression. Can you see, all of you? Can you see, all of
Yes,
you?
sir.
Yes, sir.
Something like that. You do like this, and G you can take it 1. So what I'm going to get again, ln 1 minus this, essentially, isn't it? It's
Yes, sir.
ln 1 minus z, because epsilon is
Yes.
0. So what I'm going to get is actually a minus ln 1 minus z or 1 minus z, but of course I have divided by volume, so I'll have something like this. Is this clear? Similarly, this is for the P by kBt. Similarly, you do the same thing for your number of particles. So your number of particles n by v is actually, it has to be a positive quantity, of course. Go and check this expression. Then I have a term coming from for epsilon equal to 0. I have to divide by volume, of course. What is that? It is going to be 1 by, you know this, z inverse minus 1. And what is this term? If I just manipulate this term, what I'm going to get? It is nothing but 1 by v, isn't it?
Yes, sir.
I'm not doing this because this is very okay. So I have now these two terms here. So just now look at this expression. See, when you're, for example, when is z is very small, what will happen to this expression? Tell me.
Which expression?
Z is very small and you are hitting the classical limit. Hitting the classical limit. Basically, your high temperature limit. No, you are at high temperature limit.
Yes, sir.
So this term is going to be what? The last term, this 1 over v, z by 1 minus c.
0. Nearly.
Because this is 1 over n, no? Volume is number of particles, scales as number of particles. And this one is, you know that it is z by 1 minus z. 1 minus z is like 1. So, and z is small. So this is actually vanishing. Isn't it? Small.
Yes, sir.
Very small. So this part has a very small contribution when your fugacity is less than 1. Okay, but if your fugacity increases and if z is now becoming much greater than say 0 and is approaching 1, what will happen?
Blow up.
Yes, you'll have a problem because when z becomes 1, this term will blow up, isn't it? This is important and diverges. And this happens when your temperature is
Low.
what? Small, actually small. And actually when your temperature becomes 0, this happens. Okay, at 0 Kelvin, ideally this term will blow up. Okay, is this clear what I'm saying? So I can now write down this expression as something like this. I just multiply both sides by v. What I have here is n equals to ne, because this has all the levels states above epsilon equal to 0 plus n0. And your n0 is okay, and your ne is, let me write down one more time. Okay, is this clear what I'm writing?
Yes, sir.
So what I am doing here, I am just writing the total number of particles as sum of two terms. One is number of particles in the epsilon equal to 0 level and the rest which are in the excited state. So basically this is number of particles in the ground state, no?
Yes, sir.
Okay. So but now if I decrease my temperature, what is going to happen? Can you see from here? This is something strange is happening here. When temperature is large, this term is negligibly small, isn't it?
Yes, sir.
So the main contribution comes from the excited state, no? Population in the excited state, not the ground state. But as you cool down your system, what do you get? What do you see here?
Almost
you
all
cool it down,
particles are in zero state.
you see that when you approach a very low temperature, what is going to happen? That the most of the contributions will come from the zero state. So the epsilon zero level gets densely populated. Okay. So basically as T decreases, the epsilon equal to zero level gets densely populated. So all the particles will come down to the ground state and they will form, collectively they will form a condensate, and this is called Bose-Einstein condensate, and this phenomena is called Bose-Einstein condensation. I think you guys had I think learned this somewhere, I'm sure. Heard this somewhere, I'm sure.
Yes, sir.
May not be taught, I'm not sure it is taught. Was it taught anywhere in other courses, in chemistry or in any other course? Some people have taken courses in physics, no? This is called BE condensation, no? Or BEC, isn't it?
Yes, sir.
And this is fantastic. See why fantastic? Because all the particles are coming and down to the ground state, and not only that, physically they also start overlapping, and they form a fourth state of matter. This is called. And this is called Bose-Einstein condensation. How many of you had heard about it? Tell me.
Yes, sir.
You knew this, no?
Yes, in a non-rigorous manner.
In
Not very rigorously, in hand wavy arguments.
it is taught in somewhere in some course. I don't know. Maybe it is taught. I have no idea.
Sir, is this
Yes.
called plasma? What
No,
you're
it is
talking
not
about?
plasma. It is not plasma. It is Bose-Einstein condensate. Loosely, one can call the fourth state of matter. It is not a fourth state of matter. I'm just calling it. It's a new state of matter. Rather, I'll call it new state of matter. Okay. And now, whatever I've taught so far, this we have a contribution from an Indian scientist whose name is Satyendranath Bose. Okay. So, how many of you know about Bose? SN Bose.
Yes, sir.
There are two famous Boses, no? Like at least two in India. One is Jagadish Chandra Bose and another is Satyendranath Bose. So Satyendranath Bose was born in 1894. Okay. So Satyendranath Bose was born in 1894, and actually what he did, I think everybody should know that what he did was some problem with this. I cannot write. There's a lag. Yes. Okay, so there is something called black body radiation. I think everybody knows about it, isn't it? I think you know.
Yes, sir.
And there is a formula called Planck's formula for black body radiation. Okay, and it is based on an assumption that okay, the energy, the photon, the light are made of photons, and these photons are actually packets of energy. Their integral multiple of something like h nu, isn't it? Nu is the frequency, h is Planck's constant. So this is not continuous. The spectrum is not continuous. So a discrete spectrum, and with that you can explain things. because if you plot your intensity as a function of lambda, it passes through a maxima. There is non-monotonic behavior, okay, which cannot be explained using classical electromagnetic theories. So Planck explained this, assuming that energy of light occur in quanta, in packets, okay. I think you know, all of you. Then actually it was Satyendranath Bose who derived this, derived this, and while deriving this, he came up with this statistics, a new statistic. He did not realize, he sent his work to Einstein, and Einstein realized it, and he published it along with Bose in a physics journal, and then he later wrote 2 more papers. And this thing collectively, and he also actually, Einstein is a person who actually pointed out that, okay, if you go to lower temperature, there is something like what I showed you, B condensation. It was a theoretical prediction long back, okay. So you have contribution from Bose, who derived this statistics, but Einstein is the first person who actually understood it, the physics, okay. So there are actually nice YouTube videos on this, you can go and watch. But before that, I'll show you one thing. I hope you can see. This is from Wikipedia. Okay. So this is called 5th state of matter, not 4th, 5th state of matter. Okay. Anyway. Okay. So basically, this is a gas of bosons. Can you see? I have to magnify.
Yes, sir, perhaps a little. Yes.
Yeah. It is from the Wikipedia. It says that, okay, if you go to low temperature, very close to absolute zero, a large fraction of bosons occupy the lowest quantum state. I showed you right now. Okay. You can explain this, that the wave function interfere and other things, which is beyond this course. It was first predicted in 1924-25. It is actually before the proper new quantum mechanics started. Schrodinger and Heisenberg, they're just starting quantum mechanics by Albert Einstein, following the crediting a pioneering paper by S.N. Bose on a new field now known as quantum statistics. So the quantum statistics or quantum statistical mechanics started with this, okay. So basically, Bose first sent a paper to Einstein on the quantum statistics of light quanta, now called photons, in which he derived Planck's quantum radiation law. You remember the Planck's quantum radiation law? I think all of you know. It is taught in quantum mechanics, also in other courses. Einstein was very impressed, and he translated the paper himself from English to German and submitted to the Bose. It for Bose to this physics journal in German physics journal, which was published in 1924. Einstein also, I think, extended Bose's ideas into other papers. And the result of their effort is the concept of Bose gas governed by Bose-Einstein statistics. So it was actually a prediction, theoretical prediction. Now what happened that bosons example includes photons. Of course, this like black body is an example. Another example is helium-4. So actually helium-4 also undergoes a transition, which is shown by this guy, Fritz London, who proposed this Bose-Einstein condensation as the mechanism for superfluidity of helium-4 and its superconductivity. So there is a phase transition of helium-4 at very low temperature. It goes from helium-1 to helium-2, 2 states of helium-4, because helium-4 is a boson. So this transition is also something like a B condensation. Okay, so it's like a phase transition. You can see, you hit a temperature, suddenly all the particles come down to the ground state. Okay. So actually, you can compute what is the velocity distribution data, and you can see that this is a gas of rubidium atoms. Okay, and you can see that as your temperature drops, your after further evaporation, just after appearance of the condensate, and after further evaporation, a sample of nearly pure condensate is formed. Actually, what happened that in mid-90s, these people, Eric Cornell, Carl Wyman of University of Colorado Boulder, and around the same time, Wolfgang Ketterle from MIT, they produced this Bose-Einstein condensate. These people did it with rubidium, Ketterle did it with sodium, and they started a new area of physics which is called ultra cold atoms, and they got the Nobel Prize. They received the Nobel Prize in physics for the year 2001 for their experimental verification of Bose-Einstein condensation. This was predicted in 1924-25, and it was experimentally verified in 1995. So how many years? 70 years, isn't it?
Yes, sir.
And we have contribution from India in this. And this particular got bosons because Bose name is now associated with bosons. And this is nice. And then after 6 years in 2001, they got the Nobel Prize, these people. I can show you the Nobel citation. I think I should have it here. These are the people: Eric Cornell, Wolfgang Ketterle, and Carl Wyman. They shared the prize, 1/3, 1/3, 1/3. It says the Nobel Prize in Physics 2001 was awarded jointly to Eric A. Cornell, Wolfgang Ketterle, and Carl Wyman for the achievement of Bose-Einstein condensation in dilute gases of alkali atoms, and for early fundamental studies of the properties of the condensates. Okay, so it's a fantastic achievement. And also chemists are also trying to do this similar things with molecules and other things. Okay, very, very important area of research in condensed matter physics. Okay, so we'll go back and then continue what we're doing. So where are we? We are here. Maybe I'll show you a video. I think not a bad idea to show a video and enjoy the video. I hope you can see and hear. So it was nice, no? The video.
Yes, sir.
I hope you could see the video. Actually, you can go to the go to Google and you get many more things on this B condensation. Okay, so let us write down this P by kVt. So if I write P by kVt, P by kVt is going to be equal to minus twice pi by h cube twice m3 by 2. Now I'm just writing the integral. So what I'm saying that, okay, my integral I'm writing like that. So I have beta epsilon, no, which is actually your p square by twice m kVt, and this I'm calling x. So basically what I have, beta d epsilon is dx. Okay, so this will give you, if I, the d epsilon becomes, if you do things properly, the epsilon to the half will become x to the power half ln 1 minus z e to the power of minus x, but then your dx becomes beta times d epsilon, isn't it? Sorry, d epsilon becomes, sorry, 1 over beta times dx. Okay, and also your epsilon to the power half is actually x to the power of half divided by beta to the power half. So I'll get 3 by 2 here. Is this clear?
Yes, sir.
I hope this is clear. This is a very small thing. And this whole quantity, actually I will write it as something like this, which is equal to, this is equal to 1 over something like lambda cube times g 5 by 2 z. What is that? We'll do that in, I'll tell you in few seconds what is that. And similar thing you can do with n minus n0 by v, which is your n excited by v, and this is equal to, actually, you know, that twice pi by h cube. You do the same thing. Okay, and this one is written as 1 by lambda cube g 3 by 2. Okay, so I have these two expressions. I'll tell you what is this in a
But
minute.
in the B by cavity, there should be the extra term also, right?
Yeah, I'll tell you why there is no extra term. Because I put that extra term 0. Here, I should have another correction, isn't it? But this correction is in the order of, see, what is that? This is z minus 1 minus z, isn't it? And this is equal to n0. You had, remember?
Sir, in B by cavity, it was like log 1 minus
Yeah,
z,
so
right?
I'm saying log 1 minus z. So your z is n0 by n0 plus 1, isn't it? n0 plus
Yes,
1. Is this clear?
yes,
So you got log 1 minus z is ln 1 divided by
in 0 plus 1.
n0 plus 1, isn't it?
Yes,
But you had a minus sign here, so a minus sign here will give you ln n0 plus 1 kind of thing. But you had 1 over v there. You remember 1 over
yes,
v?
by volume, yes.
1 over v was there. So basically you have a scaling like 1 over n ln n. And in the thermodynamic limit, when n is large, this is 0. Thermodynamic limit, huh?
Yes.
When I'm dealing with a thermodynamic limit, n is large. So I'll have only this expression. So here I have to define few quantities. Lambda. Lambda is given by this. This is a name. This is called de Broglie's thermal wavelength. But I'm not writing it here. That doesn't matter. But this g is a function actually. G nu z or g nu z. These are actually called Bose-Einstein functions. What are these? So if I write down the expression, so don't get scared. I don't expect you to remember. It's a gamma function, gamma nu. Okay, this is how it is, and this is equal to z plus. So now, if it is 3 by 2, this is fine. Now 3 by 2 minus 1 is what? X to the power half. It is matching, is it here? Isn't it? It is matching. What about 5 by 2? Is it matching? Go and check. You can go and check. Okay, now, for example, upper bound of, say, g 3 by 2 z. What should be the upper bound for a given nu is given? Nu is 3 by 2. Can anyone tell me what will be the upper bound to this function? Actually, you know this because what is the possible value of z? Z is varying from 0 and 1. So maximum value of z is 1. So actually, I'll have g 3 by 2 1, which is called zeta 3 by 2, and this is actually 1 plus 1 by 2 to the power 3 by 2 plus 1 plus 3 by 2 plus dot dot, and if you calculate this, it will give you something like 2.62. Okay, so this is the upper bound to that function. The upper bound to that function. Okay, so now can I write down the expression for the particles in the excited state? What will be the expression? Ne. What will the expression? Remember, how many of you remember this? Just we have written here, no? V times lambda cube, V divided by lambda cube times this, isn't it?
Yes.
In general, it is like this for a given value of z, but if fugacity is 1, if, then what is the value? Now fugacity 1 is what? What does it mean? Fugacity 1 means what? This is quantum.
Quantum, yes.
So this will give you this g will be replaced by zeta
3 by
3
2.
by. So basically, then there will be I can write in general that Ne has to be less than equal to V by lambda cube this is the number of particles in the excited state at z is equal to 1. Is this clear? If you have problem, tell me what I have done here.
So it shouldn't it be greater than
Greater
equal?
than or less than?
And very low temperature, uh, nearly all particles are in energy ground state. So that is the least possible number of particles in excited state,
What
right?
others are thinking? Others are there because I will just finish in a few minutes because I don't think I can continue. I have to do more things. I don't think I have time today. What others are thinking? Is it what Anish is saying is correct, or it should be the other way?
Sir, intuitively, he's correct, I think, because the ground state, because at very low temperature, all would be in ground state.
So if your
So-
temperature is low, so at low temperature, all in the ground state. But what is any
In the excited states, all the
excited states? So at when temperature is low, what will happen? The most of the particles will be in the ground state. Very less number of particles in the excited state.
Yes.
So at low temperature, what is the number of particles in the excited state? Tell me. Tell
This
me.
expression V by lambda cube is I
This
of
one.
V by 2.
This one, isn't it? So
Yes.
at any finite temperature, your number of particles in the excited state has to be less than that, isn't it? The left hand side is this number of particles in the excited state. This one.
At any finite t greater than 0.
Okay.
Yes, sir. Yes.
And on your right, what is this? This is
At t equal to 0, the number of
when you are
particles.
approaching t equal to 0, isn't it? So any finite temperature which is greater than your t equal to 0, what do you expect? More particles in an excited state, isn't it? Think about it. So
Yes.
you're lowering the temperature, the particles are coming down from the excited state to the ground state.
So NE is decreasing as we reduce the temperature.
Yes, isn't it?
Yes.
So at any NE at higher temperature should be the number of particles in the excited state should be higher than the case when the temperature is low.
Yes, that is correct.
And this is exactly what I've written, isn't it?
The sign should be greater equal to,
Why?
because NE at t greater than 0 is greater than NE at t equal to 0. Is that right?
Yes, you're right.
And
Yeah.
NE at t equal to 0 is this v by lambda cube psi of 3 by 2.
Yes, you're right. I think if I write like this, we'll stop here today. Okay, I think I don't have time. So this sign will do in the next class. Actually, it depends on how you interpret this. Okay.
I think we can get a less than inequality for n0.
Okay, so we'll do it in the next class. Okay, we'll stop here, right? Because I don't think we have time. Okay, I'll now.
Okay, sir.